So Matthew Kenworthy is an associate professor at Leiden University, and he, in addition to searching for shadows from other stars, he uses some of the world's largest telescopes with optics that can remove the glare of the stars to reveal planets orbiting around them. He will talk about how searching for strange eclipses and young stars led him to discover giant ring systems around young planets outside our solar system. And as fun fact, he has seen Stephen Hawking at the Curry House. He has invented 2 types of sailing knot, met 2 Nobel laureates and eaten tacos with one of them, but also has been known to not tell the complete truth in fun facts. So I hope we clarified a bit of this. Okay, let's give a thanks to the nurse speaker.
Cool, thank you very much. And thanks for the introduction. And yes, I did not only meet Stephen Hawking, he ran over my foot, which was kind of irritating. Going to the Curry House, I stepped to one side and it wasn't fast enough and he kind of bounced over my feet and didn't apologise. So, clearly desperate for curry, I can understand that. Anyway, so what I want to do this evening is try and convince you that the weird shadows that I've been seeing are actually due to giant rings around planets and low-mass stars nearby in our galaxy. And you'll see this animation a bit more later, but this was actually one of the models I made was turned into an animation for the Cosmos series in America. And I didn't know about it until somebody emailed and said, I think they've got your ring system on one of the programs in America. It's like, no, they can't. They would have told me beforehand. They did not tell me beforehand. Anyway, off we go. Oops, way too fast. So, the way we think planets in our solar system and around other stars are made, when the initial cloud of gas and dust coalesce from a large cold cloud of dust and gas, you switch on the star in the middle, and then the remaining gas and dust forms a disk which spins around the star. And you can see some proto-stars with their proto-disks. This is in Orion, so you can see Orion the constellation at night near here when the skies are clear. And what you're seeing is that there's a background screen of illuminated gas, and in the foreground you see these little black dots. And there's proto-stars just about to switch on, and they'll start the radiation from them. The light pressure will clear out the surrounding disks. But we know this is where planets form. And if you were... let's see if this... I have to go closer. Gets me further from my beer. Okay, so before 1995, when I grew up, this was all the number of planets that we knew in the universe. So we had 8 planets. We had 9 planets for a while, but we voted Pluto out because it didn't try hard enough. And we had this suite of planets that we know around our sun. And our picture, astronomers' pictures of how planets are formed, is that big disk of dust and gas coalesces in the middle of the solar system to form the gas giant planets. Too close to the sun, the solar radiation pressure strips away the gas and leaves the dust, so you get the terrestrial planets, and you get the ice giants, Neptune and Uranus, hanging out on the far side. So we expected to find big fat planets far away from their central star. However, this, as Joe alluded to and showed, there are many people who are trying to detect planets with this knowledge using the radial velocity method. So you understand what the radial velocity method was. There was more than one set of astronomers in the world competing to try and do this, and there was Marcy and Butler with the American team, and Mayor and Kellos were the European team. And basically they needed to take pictures, spectra, these special fingerprints of nearby stars for weeks, months and years at a time, because you had to gather enough data to try and spot this special signal. And Mayer and Kellos were the first, as you heard from before, and they won the Nobel Prize for that. Well, Marcy and Butler looked at each other and went, hold on, 51 Pegasi b, we've got 51 Peg, we've been studying that star for years and years. They went back in their data, had a look, and sure enough, they had the planet there as well. So they had the data, they just didn't think of thinking outside the box to look for a short period planet. So we're used to the gas giants taking years and years and years to orbit around the star. This planet had an orbital period of 4 days. They simply didn't bother to set the computers to search for 4-day orbital period planets. They would have been the first if they bothered to do it. So we had the technology, it's just you need to sometimes think outside the box and have a new kind of approach to an idea. Okay, so when these very short orbital period planets were found, the next thought that occurred to lots of astronomers is, well, hold on a minute, if you've got a big fat Jupiter on a very, very short orbital period, there's a chance that it will transit the disk of its star. Now, all the planetary orbits in our galaxy are completely randomly oriented. And what this means is if you take a big bunch of hula hoops representing the orbits of planets, throw them up in the air above you, take a photograph and then run away before all the hula hoops come crashing back down on you, the photo will have a few of the hula hoops exactly edge on, which means that the orbit of the planet moves in front of the star. And of course, here's the 2012 transit of Venus. Great minds think alike, and also steal the same slides. But this is what we see. And the problem is that Venus is pretty tiny compared to the disk of the Sun, so the drop in flux is really, really tiny. So you have to have a very good telescope and a very good camera to measure that tiny distance. Furthermore, due to the relative orientation of the Earth and the Sun and Venus's orbit, this only happens twice every 108 years or so. So if you didn't see this transit, chances are most of us won't see the next transit of Venus, which is somewhere in the 2100s. Anyway, with this in mind, a whole load of astronomers went out, got their telescopes and started looking at taking pictures of the night sky, trying to see if they could see transiting exoplanets. Now we knew that nature made big fat planets very close to their parent stars. You could actually start mapping out what's called a light curve. So what we've got here is we measure how bright the star is, and every 10 minutes take another photo. And the trouble is you don't know which stars have transiting exoplanets. So what you have to do is play the numbers game. You take pictures of millions upon millions of stars every night for months on end, and then you try and look for that little characteristic dip as a planet moves in front of it. And sure enough, you can start detecting them. So this is one of the first detected exoplanet transits, and it lasts a few hours and it drops by about 2%. So the flux of the star dims for a little bit. We of course don't see the planet and the star, we just see the sun's light from the star. And so with this idea in mind, the Kepler satellite went up. And this is basically a gigantic camera with the same technology that we use in our everyday phones. So this has 48 CCDs, special light sensitive, very low noise detectors. And you can see them all clumped together here in the assembly hall. And this is the picture they took. So Kepler went out and it took a picture every 2 minutes for 4 years. And recorded the flux of 100,000 stars every 2 minutes and sent down the data to Earth. And currently we have over 5,000 exoplanet detections, the vast majority of them, through missions like Kepler and subsequent missions like TESS. Because you're looking for the light of the star and not the light of the planet, it turns out that you can do this cheaply, and astronomers love cheap things. So what you can do is you can basically buy telephoto lenses for sports games, and you can stick a cooled camera on the back of them, and you can take pictures night after night after night from the ground. And so there are many, many surveys done in the 2000s, and there are two of them here. There's the Super WASP survey on the left, and the All Sky Automated Survey, ASAS, on the right. And these were basically searching for variable stars and for transiting exoplanets based on the knowledge we had. You don't need these big telescopes to see the planets, so this was a fantastic way of really kick-starting this field. So, where do I come into this? One of the colleagues I work with is a guy called Eric Mamajek, and he's now at Jet Propulsion Laboratory in America. And at the time, he had a student who was looking at light curves. So all these telescopes, they publish their light curves. And all they're interested in is little tiny dips which last a few hours. And the rest of the stuff, there's just too many light curves to look at. So they just kind of throw them in the bin. And instead of throwing them in the bin, some of them actually stuck all the rest of the light curves online and said, knock yourself out, have a look at the light curve of a nearby star if you want to. So Mark, his then graduate student, comes in and says, yeah, there's something weird with J1407. He was looking at young stars very close to the Earth, about 300 light years away. And I'm interested in them because young stars mean that the research I do means I can take pictures of the stars and look at the planet, but that's another talk. But Mark looked and said, yeah, there's something odd going on with this star. So this is the light curve, and on the bottom axis it's thousands of days. So 1,000 days is about 3 years, This covers about 12 years. These missions have been running for 12 years, taking data. Nobody had really looked at these light curves before. And you see this, and what we see is the brightness. So at the top here are the ASAS points, and we'll now zoom in. Something weird happened with this star sometime around May 2007, and nobody noticed it. It was sitting in the database, unacknowledged. And what happened was that this star's bobbling along quite happily, and then it fades for a few days, and then it pops back up again. And then it has another thing, fades even more, goes back up again, fades completely, and it disappears for 2 weeks. The star's gone. It pops back up again, a smaller dip, a tinier dip, and it's been rumbling along, and this blasted star hasn't done anything weird since. So in the past 15 years I've been staring at this eagle-eyed. This blasted star's not done it again. And because this was recorded and installed on a computer, I didn't know at the time that this star was doing something weird. It was just sitting on a hard drive for many years. But Mark and Eric were scratching their heads, and Eric finally showed me this light curve. I went, well, that's completely bonkers, what's going on here? So what I was able to do was, one of the 2 telescopes I showed you had 8 lenses, 4x2 configuration. It turns out this star sits on the corner of 3 of the fields of view. So I got a really good student to have a look at the data, and I said, can you clean up the light curve, because that earlier light curve's a bit noisy. And so this is what it does, and I was able to get each night, so each of these little black strips is 1 night's worth of data. And if you zoom in on each of these little nights, this star is bonkers. It's been sitting there, it's been totally fine for the past 20 years, and then for 2 months, it's as if my daughter's run off to the light switch and is flicking the light switch on furiously. It's going along, it's going flat, it's gone down, it's decided it's bored, it's gone back up. This one has done a square root sign, so it's going along, turned the corner, went back down, went back up. Keeps on doing this for day after day after day for 2 months. And this is completely crackers. I've never seen a star do something like this before, and neither had Eric either. So we're all scratching our heads trying to work out what was going on. And basically, the least stupid explanation for this is that we're seeing something move in front of the star, something much, much bigger than the star itself. And it's about the size of the Earth's orbit. Not the size of the Earth, the planet, the orbit of the Earth around the Sun. It's that size. So I was able to take that light curve, play a couple of mathematical tricks, and I said, I think it's a giant set of rings, like the rings of Saturn, but 200 times wider. And so this was an animation I made of it. And what you're seeing here is the star. Everything's to scale. So the star is that size. These are all the rings, and the light's transmitting through the rings, and each time a ring moves in front of the star, the light curve changes direction. And this took me a while to work it out. And the problem is, I think about half the astronomers I give a more detailed talk for professional astronomers, and basically half the astronomers have the look that you all have on your face right now. They're going, what are you smoking and can I get some? And it's true, I realise this is a challenge. So one of the things you do as a professional astronomer is you have to write what's called a paper, and you have to give it to your fellow astronomers. And the fellow astronomers basically call bullshit on you. Whether they say, yeah, that makes sense, or whether not. I was so scared of submitting this, I sat on it for 3 months, which is completely bonkers, but I just did that. Oh my God, I'm going to look like a complete idiot if this is wrong. So I submitted it with my heart in my mouth, and about 2 months later, the reply came back, yeah, that sounds reasonable, we're totally fine with that. And it's like, what? Seriously? Giant rings, man, what are you talking about? This is completely bonkers. The other astronomer said, yeah, that's fine, I'll go for that. But anyway, what I think we're seeing is the last bit of how we make planets. So I'll describe this. What this is a computer simulation. And what you have is it's a face-on. We're looking down on those big disks that you saw on one of the first pictures. The star's hidden here in the middle, and this is a computer simulation of the dust and the gas and how it flows around the star. And what we do is we're deliberately fixing it so that the planet is on one side. Now in reality, the planet's orbiting around the star, but you get very dizzy and you can't see what's going on in the simulation. So what we do is we spin the camera to follow the planet as well. And what you're seeing is the gas and the dust here are orbiting around the star, because the star's gravity is winning the fight. But if you're too close to the planet, the gravity of the planet is holding on to the dust and gas more strongly than the star's gravity. And what you get is a little thing called an accretion disk, a circumplanetary disk. So this thing is the dust and gas are being funneled on, and it's being slowly spiraling down, and it's falling into the planet and forming the planet. And this doesn't take that long. It takes about 1 million years, which is kind of a blink in the eye. So the sun is a middle-aged star. So if it's my age, this is about when I was about 3 weeks old. Okay, so this is super young. Stars make planets really, really quickly, and they get the job done quickly. But what I think we're seeing is we're seeing one of these circumplanetary disks move in front of the star, because the size is about right. It sort of works. And I've sort of convinced most of the astronomers I talk to about it. So I'm kind of on the fringe on this, but it's tremendous fun. It's way more interesting. So what you see is something like this. This is the cartoon version of that. You've got the circumstellar disk, and you've got the circumplanetary disk with the planet in there. At some point, the circumstellar disk goes away. It either falls onto the star, falls onto the planet, or gets blown out of the system. And once that happens, you stop feeding the circumplanetary disk. And then something weird happens. What happens is that gravity takes over and it forms moons, exomoons, moons orbiting around that protoplanet. And it carves out gaps, it carves out racetracks around the planet. And that's what I think we're seeing moving in front of the star. We're not seeing the moons, they're way too tiny, but we're seeing what the moons are doing to the disk. And so that's what I said. Oh, I said we've got a Mars-sized exomoon. And again, the person refereeing it went, yeah, that's totally reasonable, go for that, no problem. Thanks. So yes, at some point this dust and gas will disappear or make moons, and then we don't see it again. So there's only a small window of time. So what I did was I immediately started looking for light curves of young stars, because this happens when they're 3-week-old babies. So I went out, looked across the sky with several very, very patient students who looked at an awful lot of light curves. I think a couple of them have left astronomy and never want to see a light curve again. Don't blame them. But
enormous as they are shockingly thin.
you can
If the ring system of J1407B
so this is what the animation looks like. This is what it would be like to fly through this ring system. And it's not too bad. They've got the planet way too big. The planet would look proportionally much, much smaller, but it's not as photogenic. But this is what the system would look like. It would be a giant ring system. If this ring system was around Saturn, it would be so large, it would be 10 full moon diameters across. It would ruin astronomy for half our year. We wouldn't be able to see the night sky because this thing would reflect so much light towards us. It would ruin astronomy. Anyway, so this is J1407, and the planet, which I haven't found, is J1407b. That's a whole other load of woe for me, which I won't bore you with. But really, it's tedious. So the other thing, meanwhile, people are running off and building more space satellites looking for exoplanet transits. And I'm not interested in exoplanet transits. They're pretty boring. Don't tell anybody else I said them. What? Somebody said that. Jinx did say it. So TESS is another satellite which is the successor of Kepler, and it's been generating light curves. It's been looking at stars all over the sky, and it's been finding lots and lots of transiting planets. There's a star called Beta Pictoris, and if you're an astronomer, it's a famous star. It's relatively nearby in the galaxy. It's got 2 planets orbiting around it, and my other job is taking pictures of planets, and I've taken pictures of this planet. And this is the light curve from TESS. Now, TESS's precision is so exquisite, what you should be seeing is a completely flat line. You shouldn't see any wiggles in this at all. This is what the data from the TESS satellite looks like when we downloaded it. It looks like horrible junk. It looks somebody's like screaming at the screen. And that's exactly what's happening. The star is ringing like a bell. The star oscillates. And it's oscillating like a glass. Literally, the surface of the star is going up and down due to the internal motions of the star. It doesn't actually shatter. That would be interesting and very brief to watch. But that's what's happening. This star is ringing like a bell. It's singing out very pure frequencies that we see of cycles per minute. And so what happened was that a very good master's student who I was working with another professor. And it turns out the professor, she was an expert at removing these pulsations. So several other groups downloaded the data, looked at it, went, can't be bothered, and dropped it. My collaborators downloaded the light curve, said, oh, delta scuti pulsator, we can clean that up, press the magic button. And on Saturday morning, I got an email from the master's student saying, hey, I found this weird looking light curve in Beta Pictoris, do you know what it is? And I spat out my coffee. It was like, oh, interesting, you know. There's this shark's tooth sitting right over there in one edge. And there's another shark's tooth, but it's hidden just there. And this shark's tooth was predicted over 20 years ago. This is a cometary transit, so there are giant comets in this system, and the comet has moved, a comet, much, much bigger than any comets that we've seen in our solar system, has moved between us and the star, and we're seeing the tail. We're not seeing the head of the comet, we're seeing the debris from the tail moving out in front. And so this is what we've got. Basically, these are supermassive ice balls, they're evaporating, and the dust out from their tails moving in front. And so it was one of the first detections of exocomets. So this was just a curious student looking at data which other more professional senior astronomers had totally skipped. They looked at it and went, can't be bothered. The student, knowing no better, actually dug in, sorted out the data, removed the problem, made a discovery, and we got a great paper out of it. So this is another wonderful thing, right? If you just think outside the box, you can discover loads of surprising things. Anyway, so this was the prediction. So you saw the shark tooth before. This is a 23-year-old science paper, and it's exactly the same shape. It's predicted, and we beat everybody else to the punch just because it was the right combination of people in the right time. It was really cool fun to do. But it's not a ring system. I'm after ring systems. And so what I've been discovering is everything which isn't a ring system but still makes a weird shape in front of the star. So, back to Kepler. This is another light curve. Now you know what a light curve looks like. It's number of days on the bottom and how bright it is compared to the normal brightness of the star on the vertical axis. And what you see is this star is spotty. Young stars are very young, they're very spotty, and they spin fast. They rotate every few days. The sun rotates every 28 to 30 days. These stars rotate every 2 to 3 days, and they've got spots which rotate in and out of the line of sight. So you see this nice little wiggle. But something wonky happens to this star for about half a day, and Kepler caught it, and it got rejected. All the Kepler people are interested in our transiting exoplanets. So this deep eclipse, 80%, they just went, not interested, threw it on the dog collar. If we zoom in onto this, it definitely does not look like a transit of an exoplanet. There's a deep, sudden drop, it sort of piddles around a bit, and then slowly comes back up again, and the star carries on before. And the people who first saw this, it wasn't people working with me, but they scratched their heads for a few months, and what they came up with is that we're seeing a teeny tiny disk. So this is a mini version of the disk that we've seen before. So the red circle here is the star, and the grey ellipse here is their model of this tilted disk moving in front of the star. And sure enough, as the model progresses and the disk moves in front of the star, it reproduces the light curve accurately. So even though we can't see these little disks, we can see the effects these little disks have moving in front of the star. And a student I worked with last year, she found another similar eclipse. So she found, I think she found this transiting system. So we've now found 3 of them. And we're not quite sure why they're still there. They're so teeny tiny, the radiation from the star should have blown them away. There's almost certainly a planet sitting in the middle of them, holding the disk together and stopping it from falling apart. And we haven't seen these move in front of the stars again, even though we're desperately searching for more clues as to the things moving in front. And this is kind of weird. We're finding, I've been chasing these for several years, and more of these light curves are starting to pop out because we've got so much data, but there's a vast amount of data and not many people to look at it. And it's a surprisingly hard thing to ask a computer to do. You can say, can you find me a light curve which is flat, and then it's got a deep bit, and then it's got not such a deep bit, and then it goes flat again, and it's not too wobbly. I can describe it fairly quickly, but trying to get a computer to do it has been surprisingly difficult. I've tried. Anyway, we found 3 of those things, and then 2 years ago in Christmas, it came home to me. There is a completely unrelated all-sky survey looking for supernovae. They're looking for stars that explode in distant galaxies. As a side effect, they flag every so often the stars which start fading, stars which simply start switching off by themselves, and they say, hey, this is kind of weird. And they show this one, which the phone number is J0600. It's about 500 light years away, it looks exactly like our sun, and it just started fading just before Christmas 2019. And I was able to ask a lot of very, very patient people to take pictures of the star over the next 2.5 years. And this is the light curve on the top, all this noise here. And I think it's a ring system. So I think that's one end of the ring there, that's the other edge of the ring, there's the inner ring, and then there's a central bit there. Now, if you believe me, then God help you. But it's tremendous fun to do this. So I'm chasing these down. This is still ongoing research, believe it or not. I don't have a nice end to this story. I'm trying to find more and more of these things as time goes on. I think these are just super cool. When I was a kid, I was always thinking of rings around planets. I thought, oh, wouldn't it be awesome if we could see them around other stars in our galaxy? And you know what? I think we actually can. So, I was delighted when this happened. I went, yeah, finally we've got all these ring systems, and so I've been trying to work with other astronomers to make sure that I've not convinced myself otherwise. Anyway, so this is what I think it looks like here. Basically, we've got a planet on an orbit around the star. The planet has these big rings around it, and this is much, much bigger than the J1407 system. And this thing has moved in front of us, and it's slowly moving out of the way. So I'm still trying to get data and basically see if I can see the signatures of moons forming in there. Pretty cool fun. Anyway, can we take pictures of these things? So I think for the closest possible systems with closest geometry, this might be just about possible to do with the extremely large telescope. So we have the very large telescope, this is the extremely large telescope. Here in Leiden, we're building one of the first cameras that will go onto it in a few years' time. To get an idea of this, this telescope is about the size of the Burcht behind us, and it would actually tower over the local church nearby. It's ridiculously huge. This thing is a stupidly big telescope with a mirror 40 meters in diameter. If you think the naming is crazy, there was a serious proposal for the OWL, which was the overwhelmingly large telescope, which is 100-meter diameter, and it's still on the drawing board, and the name still sticks. Anyway, I've convinced you that we're seeing transits of really exciting things in ring systems, and I'll leave it for any questions. So thank you very much for your time.
Instead of looking at light curve in the star, potentially look at a very small patch of the night sky, for example 4 or 5 stars in each other's neighborhood, so you can like verify whether you have a disk.
So can we look at the nearby stars in the field of view and see if they move in front? So these disks are still tiny compared to the distances between stars. So all you see is one star fading away and the nearby stars stay the same brightness, and that's what you'd expect. So unfortunately that doesn't happen.
How symmetrical do the light curve needs to be before the science says it's definitely a ring?
How smooth and symmetrical does the light curve have to be? Is it kind of this symmetric? Like that. Unfortunately, I don't have a good way of being more mathematical about it. You sort of squint at it and go, yeah, that's kind of symmetric, and it's lasted a long time, and we haven't seen any other eclipses in the past few years. I'm afraid it's as weak as that at the moment. I don't have a hard and fast way of finding them. Eyeballs are the best way of finding them.
Do we have any other way to corroborate your vision, like in addition to a light curve?
Oh, so what else can we do? So it's not just the light curve. So the J1407 system has been the albatross around my neck. I have thrown the world's largest telescopes at this to try and take a picture of the planet in the middle. I cannot see the damn thing. I know it's there, the rings are there, they're being held together by the gravity of this planet. I cannot get a blasted picture of this thing. It has driven me nuts. I've written several papers where I've gone, no, didn't see it that way. But yes, you're quite right. So we should be able to take a picture of the planet if it's a very young system, because the planet is still glowing from the heat of formation. I've had zero success. It's been so frustrating. But good fun.
This one is supposed to take it, right?
This one may well be able, we'll definitely take a picture of the J1407 one, or I'll eat my hat.
I have noted.
Oh god, somebody will hold me to that. Yes.
Do you expect an increase in brightness when it translates on the other side of the
Oh, good question. I've got somebody hooked. Yes. Okay, so when the ring system goes around to the other side, as you'd expect, there is now starlight shining on those rings, and it's bouncing back towards us. So I've tried to look for it in the J1407 system, but the trouble is we don't know how long it takes to orbit the star. And also the signal's fairly tiny. It's about 1/10 of 1% is the reflected light. And the trouble is the star is young and spotty. So that signal washes out any kind of reflection. But I have looked for it, haven't found anything, but haven't ruled it out. But yeah, great question, thank you. Right at the back.
Unless you have multiple transits, how would you be able to distinguish between a planet closer to a star with massive rings or a planet much closer to us, like a rogue planet maybe?
Okay.
Smaller rings.
So could it be a planet floating between us and the star? Yes, it could be. The trick is, if it's too close, there's a thing called parallax, and it's because the Earth orbits around the Sun. And so if there was a ring system very, very close to us, the speed at which it moves in front of the star would be all wrong. And we could tell that very, very quickly. But yes, so one of the things I did was made a sanity check that I wasn't looking at Saturn. I had somehow accidentally got Saturn in the field of view of the camera. And then we can play a couple of tricks. Basically, it's like if you look at the sun and it's a bright day and then you draw the curtains in front of the sun, the speed of the curtains tells you how quickly the sun dims. And we can do exactly the same mathematical trick here. So if the star fluctuates very, very quickly, the stuff moving in front of it must be going across it very fast, and therefore it must be close to the star. It must be in a very small, fast orbit close to the star. And I've played that trick.
What do you consider the next most probable thing that can cause a signature that you're now interpreting as the...
Right, so if it's not rings, what on earth is causing this? It's a good question, and I've had a lot of professional astronomers give me the stink eye, saying, oh, it can't be rings, and I go, yep, right, explain it elsewhere. And there's a long, long pause, and a couple of them say, I'll get back to you, and they've never got back to me. So it's the least insane explanation which is consistent with the data. But if you can come up with an alternative explanation, so there are things called carbon stars which burst out clouds of debris, so Betelgeuse got famous because it started fading, but that's a supergiant star, and I know all these nearby stars are solar type stars. So it's not that, it's not one of those stars.
I'll get back to you.
I wish it would be easier, make my life easier, I can get on with other things.
So in the Lagrangian points of Jupiter,
Yes.
there are the Trojans, like these groups of asteroids that are like going there like over
Sure.
density. How will those do a signal?
Could those do the same? Okay, so the question is, so if you look at Jupiter, if you go 60 degrees ahead of Jupiter, there's a clump of asteroids. There's kind of a gravitational stable point formed by Jupiter and the Sun. And it's an equal-sided triangle. So there's a leading Trojan point and a trailing Trojan point. And that's true for most systems. Could it be a big pile of stuff sitting on the Trojan point? And the answer is yes, it could. But the trouble is I see very ring-like structures. It's highly organized. The stuff in the Trojans is just sort of wobbling around, being pushed around by the gravity of the other planets. So it's a kind of higgledy-piggledy mess. These look like very organized rings moving across the disk of the star. And they're honking huge. That's the one thing which kills all the professional astronomers is if you multiply 56 days by the speed I get, it's the diameter of the Earth's orbit. It's a big thing. No matter what explanation you accept, something really big is moving in front of the star, and you can't get around that. That's kind of the one crotchety point which everybody falls over on.
Yeah, one last question maybe over there. What about a spaceship?
Professor Van der Marel, that's a mean question to ask me. Is it a spaceship? No, it's not a spaceship. Just for everybody else, if you say it's aliens, that's the weakest possible excuse to go for. It's like, yeah, I don't know what did it, it's the aliens. No, it's a natural, it's almost certainly a natural phenomenon. The case of JO600, I could do a special trick and measure the color as it the color of the star as it changed, and basically it's totally consistent with very, very fine dust. So very, very kind of fine dust that we know orbits around stars. that's what's moving in front of the star. So you go for the natural explanation first before reaching for that explanation. Thank you. No, I'm not even going there near that height. Thank you. Cool, I convinced everybody.
Okay, so we're going to finish, this is the end of our event. We're going to thank the speakers again.